Hey everybody, this is Larry. This is me going over the contest problem for minimum possible integer after at most k adjacent swaps on digits. So this problem asks you to, given a number and it's a big number. By that I mean it goes to 30,000 digits, I think, and assuming that there's no leading zeros, though I think it doesn't actually matter. Um, Try to minimize the number, right? So the way that I did it is just by greedy, but it's kind of hard to kind of do that proof, at least for me during the contest. So the idea is that, well, you just keep on asking yourself, at least that the way that I did it is I keep asking myself, what is the smallest number that we could move to the front, right? And if we can, then we move that to the front, and now we have a sub problem of minus some amount of swaps, and you know and the rest of the number, right? And the reason why that this works is, and we could go illustrate it with an example, and the reason why this greedy works for this problem is because the way that this is, this will take a lot of practice on these kind of problems. For me, it's not necessary that I saw this problem and I'll be like, oh yeah, of course, this, like I prove it in my mind. Though it might feel that way, but it's just more that if you practice enough, you see these kind of problems, you kind of gain a sort of intuition about how the numbers relate to each other, right? And in this case, well, the question is, let's say you have two numbers that we can move to the front, right? Let's say our k is equal, our k is equal to infinity. Doesn't really matter, right? Some big number. And then the question is, okay, let's say there's a 0 here, and then there's a 1 here, right? Let's just move, change, whatever, doesn't matter, right? Well, is there ever a case where you want to move to 1 instead of 0? Well, the answer is yes. The only time you want to do that is if you don't have swaps for the 0 and you have barely enough swaps for the 1, right? And you could kind of make it, to yourself where like, okay, if there's 0, then that means that, you could look at the prefix, which is, this 0 plus the rest of this string, right? So this is what happens after you move to 0, and this is what happens if you move to 1, right? And if you look at these two numbers, there's no way to catch up later on, unless you move to 0 back to the front, but then that's just, then you have just done it to begin with. And that's kind of the greedy intuition that I had, because I've solved different problems where you have to figure out how to, minimize a sequence of, digits or something like that, right? So that's kind of how I came to it. Implementation is a little tricky, obviously, and it's gonna, but the other case that we have to consider, of course, is, let's say we have this thing, right? Let's say the 2 zeros, right? Here, for example. Well, is there ever any time we want to move the back 0 before we move the first 0? No, right? Because again, because of greedy, which you still have to convince yourself. But if you move the back 0, then and then move the front 0, it's still going to be smaller than moving the front 0 and then moving the back 0, right? So is that kind of intuition that lets me choose one digit at a time, because to minimize the final number, we want to greedily, if you will, minimize the first digit at a time. And you could prove to yourself, right? If you could get a 0 in the front, no matter what, no number's going to beat it, and then you keep on doing it that way, right? And if you can get a 0 in the front, then you try to put a 1 in the front, or so forth. So that's kind of the strategy and how I think about this problem. Yeah, and in terms of implementation, that's like you could say is greedy, and I think that supposedly in the contest, some people have written n-square algorithms and they got got AC or accepted. I mean, I didn't do it that way, so I'm not gonna go over that type of solution. And also, I think there's some like micro optimization that makes it maybe passing. But anyway, like you don't learn that way per se. Well, maybe you learn the greedy part, but still, and for a contest, it's fun, it's just thrilling. But at the end of the day, the only score is whether you learn or not. So for here, I'm going to go over my solution that I did during the contest. And afterwards, you could see me do it live. No commentary this time, though, because it's been a long day. But anyway, so basically what I did was I created a deck, which is basically a queue, because I just pop fun and stuff like that, effectively in Python. And and then for each number or for each digit, I just put it on the matching that number, and then I use this high machinery thing called binary index tree. It's a little bit hard to kind of explain what a binary index tree is beyond the scope of this thing, but suffice to say that another name for a binary index tree is the Fenwick tree, but also people just refer to sometimes as the prefix sum tree, right? And what that means is that this is just an abstract data type where you have two operations that you can do. One is this increment, or increase by delta, but increment function where you take an index, and then anytime you increase the index by a delta such that a later query of anything that's greater than or equal to index will include the sum of all the prefix, hence the prefix sum tree, right? So that's kind of how I knew it. Count will just give you the number, the sum that is smaller than or equal to index. So without going over this, because you could use it as an abstract data type, meaning you don't need to know it if you know how it operates. I'll maybe if you leave a comment in below, maybe at some point I'll do a video on it. Let me know. But otherwise, yeah. So knowing that, we use this prefix sum tree, or Fenwick tree, to just keep track of how many things we move to the front. Because the idea is that, okay, let's say we have this long string, right? And let's say we have 5, some zeros and stuff like that, and we want to move the 0 right to the front. How many swaps will it take? Well, you could kind of show it easier. I'll show it easier by putting more zeros in the front. But let's say you have this string instead. Well, if this 0 is in the second position, then it takes 2 swaps to move to the front, right? And if there's another one here, then this takes 4 swaps to 1, 2, 3, 4. Yeah, 4 swaps to move to the front because it's in the 4th position. So then now, the problem is, okay, let's say you move this 0 to the front. Well, this second 0 doesn't need to be in the front, right? So, or it needs to be in the front, but not the absolute front. It could be minus the one that you already moved. So the way that we use the prefix sum tree is by saying, okay, let's say you could. Another way of thinking about it is that you could add all number, like looking at all the positions of. So let's say this is position 2. This is position 4. I don't know what this is, but let's just say I don't know. Let's say this is 12. Squeeze some space. Let's say this is 15, and then let's just dot this, right? And when we move the 2 to 0, right, now, because we only have to move this by 1 less, you could effectively also treat it as just subtract all the zeros. Actually, not even just zeros, every number, right? Because now all the numbers to the right of the 0 that you moved. So this was the old place. I'll put a mark here. So all the numbers to the right of it, you could think of it as, we moved by 1, right? Oink, oink. And then now you can just, subtract 1 from where everything is and treating this, the 9, as the new 0 and moving everything, right? And now that we do it that way, another way to count that is just count, well, if we have a 2 here, or a 0 here that has the index 2, then all you have to do is just count how many gaps you have in the original array. And that's pretty much how I keep track, use this thing, because now we could say, oh, there's the count function now. So every time we remove an index, we set it to +1. So this is +1, and then the count will allow us to sum up all the numbers, which means all the ones that are in the prefix before this, right? So let's say you want to move 4 next, you count all the sum of all the ones that are before that. And that's kind of, roughly speaking, that's pretty much how I did it. And I did it really lazy and greedy when I implemented, because I implemented during the contest. But basically, while we have any more swaps, and if we have any numbers left, that's what found is for. If we have any numbers left, we check, from 0 to 9. If we have a digit in here, then we just do it. Well, if there's any digits, then we just, then it's good. Yeah, if there's any digits left, then that means that found is true. That means that, we'll loop again. Because if we didn't find any digits left, and you can always prove that there will always be digits left, or k is equal to 0, right? So it terminates one way or the other. And then now this is the position that the smallest digit is in. So this could be 0, 1, whatever it is. So D, and this is a Q. So it takes the front of the queue to be like, okay, because we insert it into the queue in order, it will give us those digits in the index order. So this gives us the index of digit D, and then the smallest index, or the one that's closest to the front. And then we subtract that from the count of the prefix, meaning how many numbers are before that, right? And if it's greater than or equal to or if it's less than or equal to k, that means that we have enough swaps. If we have enough swaps, we just subtract it, we increment it to mark that as being done, we pop off the deck or queue to remove, so that next time it will be the next index, and then I just put it into the array, or well, in this case it's a string. Just be like, okay, so we know that the first digit is going to be D. And that's pretty much all I did. I looped through this to keep on getting the smallest digit that satisfies these conditions, meaning that the invariant is that we always get the smallest digit in which this is less than or equal to k. And once we're done, then we have to reconstruct the rest of the array, or the rest of the numbers that we didn't put, pop off and put on the answer. And I just basically reconstructed digit by the index, and I sort by the index, and then for each, now that it's index order, so this should be in the original order minus the numbers that we removed by popping left, and then we just put it into the answer. Yeah, so it's a very hard problem. Don't feel confused if you don't know how to solve this. I think there are two parts that you need to know to figure this problem out. One is the greedy part, which I think a lot of people did because they got the n squared part, which you can figure out yourself. The second part is just knowing about binary index tree or Figmic tree, and stuff like that. And you could maybe if I have to Google it to figure it out. But the key part about knowing about binary index tree is just these two interfaces, or this interface that contains these two methods. One is increment some prefix by some delta, or subtract if you just return a negative delta, and then count the sum of from 0 to some index of all the numbers that you have either increment or decrement before that. And yeah, that's all I have for this problem. Stay tuned for the live portion. During the contest, it's a little bit quiet because I didn't do commentary because that was during the contest. And yeah, let me know what you think. Let me know how you did this farm. And yeah, I will see y'all soon. Bye bye. Well, this is gonna be a little bit sad today, but how are people doing 3 minutes? It must be. Am I doing this stupidly? I guess so. I spent an hour on it. Okay, let's just get this right. Okay. How do you use binary index tree for this? index minus I didn't. Oh my god. I cannot. So Oh, of course you're already done. That's the answer. I can't get the C. I got Ian so quickly.